Hi, this is David Harper of Bionic Turtle with part 2 in my small series on linear regression, where I'd like to try and illustrate the most common approach to linear regression called method of ordinary least squares, or OLS. In order to do that, I'm going to use the same data set that I used yesterday, and that was a plot of customers and their spend on the lotto. So this is $28 spent by this customer here on the lotto against that customer's weekly disposable income. So we had 10 customers here, and what they spent on the lotto, their disposable income is $150 per week. Here's another 10 customers, their spend on the lotto, but they're at a higher tier of personal disposable income. This is the population. There's 100 data points here. In statistics, we usually don't have access to the population. We can graph it on a scattergram, which does reveal that there's, at least visually, a linear relationship of all 100 data points. But again, we're going to draw a sample from that, and we can draw many different samples. So here's just two. Here's a sample of 10 of the data points out of the entire population of 100. That gives us a set of data points, a smaller scattergram with its own linear regression line, and we could draw another sample, and we would, in all likelihood, get a different sample, and that would give us a different linear regression. So the idea is that although we have a single population with its own population regression function, we may have many different samples. Each time we take a sample, we'll get a different result. Each of those samples has its own sample regression function. Okay, so let's look at the ordinary least squared approach. And what I have are two sets of observations. Here's the x observations plotted against the y. We need pairs of data. That would give us the scattergram. And then we have a series of calculations. Here's x times y, so that's just the product of the two. This column is x squared. Then we have a small x, which is simply the deviation between the x observation and the average of all the x's. So right here, if we take this negative 87, that's the difference between the x observation and the average of all the x's. So that's what the small x means. It's a deviation. Same with the y. The small y is the observed y, that's right here. We have 10 different observed y's, minus the single average y. Okay, then we're almost to the regression equation actually. This column is the small x squared. So what we have here are the deviations squared, the difference between the observation and the average x. That's the deviation. Then we square it for each observation. So we have 10 different squared deviations. Finally, small x, small y, this is the cross product. It's the product of the x deviations multiplied by the product of the y deviations. So observed x minus average x multiplied by observed y minus average y. So we take the product and we have 10 different cross products. Given that we've done these two calculations, I can actually now compute the slope and the intercept of the linear regression equation. And so this B2 right here is the slope of the linear regression line, so it happens to equal 0.08, and it is this sum of cross products right here. So that's the numerator. See, I've got the equation right here for B2, and it's a fraction in the numerator. The sum of the cross products, x times y, divided by the squared deviations for x, summed. So that's right here in the denominator. So really I have this number, a sum, divided by this number. That gets me B2, which is the slope of the linear regression line. Here's the line right here, y equals intercept plus slope multiplied by x. And you can see the slope is 0.08 because it's this number divided by this number. How do I get B1, the intercept? Well, that's easy because I can use this formula here. I can simply take B1 is equal to the average y minus the slope that I just calculated multiplied by the average x. Why can I do that? Here's something about the linear regression line. That line is going to pass through the point represented by the average x and the average y. The linear regression line passes through the average of x and the average of y. Because that's true, I can use this formula here to calculate the intercept. So I now have both the slope and the intercept. Y equals the intercept plus the slope multiplied by x. And so visually, if I just move this chart here up into this area, the linear regression line is represented by the green solid, and the blue dots are the observations. So these are the actual y's. And then we could call the points on the line, these are the fitted y's, and I've got a column for that right here. And all I've done there is applied the linear regression equation. So each fitted y is simply the intercept plus the x observation multiplied by the slope. That gives me the set of fitted y's. By definition, the fitted y's all fall on the straight line. And so here's a really key part about the regression. Notice that unless a point is directly on the line, there's going to be a residual, a difference between the actual y observation and the line. So we call that the residual, represented by the small e here. And in my calculation, it's simply the difference between the fitted y minus the actual y, or the actual y minus the fitted y, really, is equal to the residual. And so here's another thing about this regression. The expected value of the residuals, or the average, if you see this formula right here, is going to equal 0. Expected value of the residuals, so that's the sum of residuals divided by the number of points, equals 0. And whoops, I can confirm that by looking right down here. This is the average of my residuals, and it does in fact equal 0. Finally, if we take these residuals and square them, so that's this column here, and again all that is the difference between the actual y, so that's a blue dot, and the fitted y, that would be a dot on the green line. That's the residual. If we square it, then we have the residual sum of squares. Or really, if we square it and add all of these together, here's we have a summation. It's the sum of the square of all of these residuals. In this case, it's almost 52. That's the residual sum of squares. And here's the feature of the ordinary least squared approach. It draws a line through these observations with the goal of minimizing this value right here, the residual sum of squares. If we were to go and draw another green line and then compute the residual sum of squares, we would inevitably get a greater value. This line has been solved for, optimized for, the idea of minimizing the sum of the square of the residual, which is the difference between the actual y and the fitted y. Okay, so it's that residual sum of squares that is really driving the derivation of this linear regression line. So I hope that's helpful. This is David Harper of the Bionic Turtle. Thanks for your time.